Questions about anything? So let's say I was finishing up that problem last time to compute the integral of t to the minus alpha over t plus 1 dt from 0 to infinity if alpha is between 0 and 1. And I drew this contour last time, and I call that a Pac-Man contour. It's a toy region. The Cauchy theorem holds on it, so the residue theorem holds, and there's one point there. If I take f of z to be the complex version of z to the minus alpha, that would be e to the minus alpha log of z. And the picture of that dotted line coming out the mouth of the Pac-Man, that's screaming to be a branch cut for the complex log function. So I'm going to take log 0 of z, where the argument of z goes from 0 to 2 pi. And remember, the plan is I'm going to close the mouth, then I'm going to let r go to infinity and epsilon go to 0, and that's going to spit me out something I can use to find the integral I want. Okay. At the end of the hour, I showed you that the modulus of e to the minus alpha, this is true for any branch of a log, the modulus of e to the minus alpha log z turns out to be mod z to the minus alpha. And there's the calculation. The fact is that the argument, which comes up in the choice of a branch, is in the e to the minus I alpha theta term, and that has modulus 1. So that has no bearing on the modulus, and it's a pretty easy calculation. So we can use that in the future when we need it. Now I want to estimate the thing inside the integral to show that integral around c sub r and the integral around c sub epsilon go to 0. So the thing on the top is we just bounded by z to the minus alpha. And the thing on the bottom, well, I have to use the denominator estimate. And the modulus of z plus 1 is greater than or equal to the absolute value of the modulus of z minus the modulus of 1, which is 1. And there's going to be two cases to consider. If the modulus of z is big, then of course, let's say if modulus z is equal to r. If that's bigger than 1, then that thing in the denominator would be equal to r minus 1. So we get one estimate in the when r is bigger than 1, and if modulus z is epsilon, which is less than 1, then that modulus would be 1 minus epsilon. So two different things. So in the case of r being big, we would get, I'd estimate that function inside the modulus of it and get r to the minus alpha over r minus 1 times the length. And notice the length, it's not all the way around. C sub r is slightly less than 2 pi r, but it's less than 2 pi r. So when it has the mouth open a little bit, that thing there is actually strictly less than 2 pi r, but at least that's a bound for it. And it turns out that alpha being positive is critical for showing this goes to 0 as r goes to infinity. That's a freshman calculus limit problem. You can use L'Hopital's or whatever you want to see it. But critical that alpha be positive for that to go to 0. And now I do the same thing for the C epsilon curve, and this time I would get epsilon to the minus alpha on top, but a 1 minus epsilon on the bottom. And now for that go to 0, by freshman calculus again, it's critical that alpha be less than 1. Because I would have, in the numerator there, I'd have epsilon to the 1 minus alpha, which is a positive thing. And that's going to go to 0. You can't use L'Hopital's rule to do this one because the denominator doesn't go to 0. It goes to 1. So it's like a trick question for freshman calculus. You can use L'Hopital above, but not there. It's much more elementary. The thing on the bottom goes to 1, and the thing on the top goes to 0, exactly because alpha is less than 1. If alpha was bigger than 1, then it wouldn't. It would blow up, in fact. So this range of alpha is needed. The right-hand end for the for the epsilon going to 0, and the left-hand side for the R term going to 0. So remember the last steps in this calculation. First, I'm going to close the mouth. And remember, I calculated that the top and the bottom don't cancel because the log term kicks in and has a different argument on the 2 pi side. On the t side, it's exactly what I want. It tends to the epsilon. It tends to the real integral from epsilon to r of the real function. But when I go all the way around to 2 pi, on the bottom side, the argument of z kicks in there, and I get an additional e to the minus alpha 2 pi term that comes in there. And the minus is because it's going the other way. It's going right to left instead of left to right. And in the limit, so I get exactly that. So that's how I'm going to get the integral I want. Now that I've done that, notice the integral goes from epsilon to r. The next thing I do is let r go to infinity. That would make the c sub r term go away. And, of course, it would make this r go to infinity when I let r go to infinity. And the next thing I do is let epsilon go to 0. That makes the integral along c sub minus epsilon go away. And that would make this term go to 0 in that limit. Maybe I should do that in green because it's part of those next two operations. And remember, that contour would spit me out as a toy region 2 pi I times the residue at minus 1. So this thing right here is the residue at minus 1 of the f of z, which I calculated last time. And so now I can solve for that integral I want and get that the integral is integral I want is 2 pi I, and I divide by that 1 minus e to the minus alpha I alpha 2 pi thing. And you look at that for a little while and realize, that looks like I can do my usual trick to turn that into a sine function. So I pull out the pi. I've got a 2i there. And I realize if I multiply the top and the bottom by e to the I alpha, I get exactly 1 over the sine of alpha pi. Oops, this is alpha pi. I alpha pi. Okay. So, that's the answer. Nice looking number for such a weird integral. Questions about that? Another standard way to do this problem that you'll see in books is to take a contour that looks like that with 3 cuts. And on each cut, you use a different branch of the log function. So let's see, on this first piece of the pizza, I would let the theta go to 0 right here. And then I'd have theta equals, say, 2 pi over 3 here. And if I'm going to use that branch, I want that to be the branch of the logarithm. Well, I can use the principal branch. So on this piece of the pi, I could use the principal branch. Log of z. Which, if you want to write it, that's log of minus pi of z. Then I would get exactly those angles. Then on this piece of the pie, I'll use a different color here. How about orange? I want theta, this theta, I want it to be 2 pi over 3. And so this theta, I want to be, what would it be? 4 pi over 3. And so to do that, I would use the log of what? Log 0 of z would work. And I would use I'd use the Cauchy theorem on the first piece of the pie, but I have to use the residue theorem on the next piece of the pie. Okay, and then finally there's one more piece of pie here. Let's see, I need another color. How about lime green? This theta would be okay, but now if I use theta equal 4 pi over 3 here, I would have to have theta equal 2 pi here. And on this piece of the pie, what would I use? Maybe I'd use log. How about log pi over 2 z? So let's see. In this for this purple one, I'd use the principal branch, which is that branch cut. For this orange one, I'd use this branch cut, and then for this green one, I just have to use something that doesn't cut into it. So I'd use those 3 different branches. But the interesting thing is they hook up, except on the last one. So whenever there's a check mark, those thetas agree, and notice the arrows go a different direction. So those integrals would cancel when I add all these up. And similarly, so that's at 2 pi over 3, that would cancel. Same thing happens at the 4 pi over 3. And then it doesn't happen at the theta equals 0 and theta 2 pi. You get different values, which means those integrals don't cancel out like they did in my previous calculation. And you'll come to the same conclusion. You just have to write more about 3 different branches of log. Sometimes you get cancellation, and in the end, the last one you don't. Questions about that? Maybe that's easier to understand without all the limits. Well, that's enough residue theorem. It's kind of fun. I didn't want to skip any of those famous examples. Questions about anything? Well, now this will be like a breath of fresh air for a while because it's kind of easy in the beginning. I'm going to talk about linear fractional transformations, which are complex rational functions that look like az plus b over cz plus d. And we would need AD minus BC to be not 0 for this to be a meaningful thing. And to see why that's relevant, note AD minus BC is the determinant. Means the rows of A, B, C, D are linearly dependent. In the case that the bottom row is equal to 0, let's see. So either the bottom, the denominator, is identically 0. That's if C and D are 0, which means that thing doesn't make any sense. Or the numerator is a multiple of the denominator. And that would mean the L of z is constant. So those are the dumb cases. Either it's not defined or it's constant. And so those are the cases we want to rule out. Let's see some key facts. I'll do them one by one. Facts, L, these things, you can think of them as the automorphism group of the extended complex plane. So it's 1-to-1 and onto. And you can think there's an automorphism group kind of in an extended sense. So think LFTs equal the automorphism group of the... it's true in the sense of Riemann surfaces. The extended complex plane is a compact Riemann surface. And those linear fractional transformations can be viewed as analytic mappings of that Riemann surface to itself. Okay, so let's see. I want to show that fact is true. So let's. There's always cases to think of. The case that C equals 0 is kind of a dumb one. Then L of Z would be equal to AZ plus B over CZ plus D. And so when and of course D couldn't be 0, otherwise that determinant would be 0. And so I can write that as AZ plus B. That's a very simple linear map. And what do we see here? We see that L of infinity, what do we see? As C goes to let's see, what do I see? L of infinity is infinity. If you think about it, what does that mean? The limit as Z goes to infinity of L of Z equals the point at infinity. So if I was going to make it continuous, I'd toss in that, I'd give it the value infinity at the point at infinity. Okay. This makes it continuous in the Riemann sphere. So setting this value makes it continuous on the Riemann sphere. Continuous C hat to itself. And of course it's one-to-one onto, because AZ plus B is one-to-one onto the finite complex plane. And so it's a simple matter to check. One-to-one onto. Then the next case to consider is the C unequal to 0 case. That's the interesting one. Then you can check that the limit as Z goes to infinity of AZ plus B by freshman calculus is A over C. So L of infinity should be defined to be A over C. That would make it continuous there. And let's see, what should go to infinity? Well, if you think about it, it's going to blow up when the denominator is 0. So L of Z blows up, which is fancy for it has a simple pole, in fact. When the denominator is equal to 0, which is when CZ plus D is 0, and that's when Z is minus D over C. So what will we write here? We want L of minus D over C to be the point at infinity. Then when we set these two things, we get a one-to-one onto map. Well, let's see, I didn't show that it's one-to-one and onto. That's pretty easy to do. So let's see. I need to show that was easy in the AZ plus B case, but I need to show L from, let's see, C minus that point minus D over C to L of infinity is A over C. C minus A over C is 1-to-1 and onto. Where there's no blowing up, it's 1-to-1 onto. And that turns out to be really easy. It's junior high math. So let's see if I write W equals AZ plus B over CZ plus D and solve for Z using junior high math. I get that Z equals DW minus B over minus CW plus A. Okay, that's the inverse. So a fact, it's going to be something to keep in mind. That should be a familiar looking thing. So how am I going to remember this fact? L corresponded to a matrix A, B, C, D. And this is L inverse. L inverse of W. And we see that L inverse corresponds to a linear fractional transformation. Let's see. This should look familiar. I switch A with D. So I get a D here and an A here. And I put minuses in the other spot. That should feel familiar. That's like taking the inverse of a 2x2 matrix. The one missing thing is I'm not dividing by the determinant. So here's an aha moment for somebody in the past. I can divide the top. If I multiply those two rows by 1 over the determinant, I would get the same linear. So let's see. L inverse also corresponds to if I multiply by 1 over the determinant. Because they would cancel out when I write. Now I get the same number in the numerator and the denominator, they'd cancel. Constant in the numerator and the denominator cancel. So there's some connection between linear fractional transformations and 2x2 complex matrices. Okay. And that's how you remember how to calculate the inverse. It's like the inverse. So that, let's see, let's call this A. If I call this A, then this looks like A inverse except for the stupid determinant. And this one is A inverse. So you can compute the inverse of, well, that's the easy way to compute it. Swap the diagonal elements and put minuses in the other spots. And skip the determinant part. But this is the determinant, and it's the same, it also represents the inverse. A fascinating thing that I'm not going to show you is that compositions of linear fractional transformations correspond to matrix multiplication. L1 composed with L2 corresponds to the matrix for A1 times the matrix for A2 for L2. So, and of course L inverse corresponds to A inverse. And not only that, but the identity I of z is 1 times z plus 0 over 0 times z plus 1. And of course that corresponds to the identity matrix. So I guess that's what you would call a group homomorphism. So this association is a group homomorphism. It's kind of cool. I should say into the group of homomorphisms. I mean into the group of 2 by 2 complex matrices with determinant non-zero. Questions about that? I guess I should emphasize this is matrix multiplication. Okay, and that's an easy calculation to check. Well, these are very useful in complex analysis for, yeah.
Question. Is there a reason we're not just holding that the, I'll say, determinant is just 1? So I think you can multiply.
You could do that when that's a different group, and it doesn't matter what it is, it just can't be 0.
Yeah, but wouldn't that be, I guess it'd be a different group, but wouldn't it be the same linear transformations?
You get the same, right, so it's a subgroup of,
Some books define it that way.
yeah, some books do it that way, and then you have this issue that, it could be plus or minus 1. You have to think about that. There's groups called SL2C and standard linear groups that are relevant here. But I don't want to get bogged down in the algebra, but the algebra can be kind of fun and exciting. For us, it's going to be more a geometric thing. And a big fact is that linear fractional transformations take lines and circles to lines and circles in the complex plane. So I'll say it this way. They take the set of lines and circles and they map them into lines and circles. An interesting thing is sometimes they get jumbled up. Okay, so a lemma for this simple fact, it boils down to sort of high school geometry in the end, but linear fractional transformations are generated by 4 basic kinds of maps through composition. So I should say via composition. As we'll see, by 4 basic maps. Let's see, number 1 is a stretch. So z gets sent to r times z, where r is a positive real number. So that's a stretch. The vector just gets stretched. 2, z gets sent to e to the I theta z. That's a rotation. Simple thing. 3, z goes to z plus something, where b is a complex number. Constant. That is a translation. You just move everything in the complex plane by b. Then there's one that's in a different category, a more interesting map, and that's z goes to 1 over z. That's of inversion. Okay, so the case is just algebra. The proof of this is just algebra, but we have this annoying situation where there's a case c equals 0. Then L of z would be az plus b. And let's see, az plus a is a complex number, so let's say that's re to the I theta. And so we see, okay, stretch by r, rotate by theta, translate by b. Okay, we see that 1, 2, and 3 are enough. So that's a trivial case. And interesting, 1, 2, and 3 take lines to lines and circles to circles. So we see that lines go to lines and circles go to circles. So that's not going to happen in the next case. Okay, so now the case C different from 0. Well, it's just junior high algebra. I do long division, AZ plus B over CZ plus D. When you do long division, you get A over C plus, here's the remainder, is B minus AD over C. C is not 0, that's good. Divided by CZ plus D. So that's the result of, let's think about the maps I need. Okay, think about your calculator, how you would punch this in. First you'd take your Z and you'd multiply by CZ. So that'd be step 1. And this C would be an RE to the I theta. So first we stretch by R, rotate by theta, translate by D. And now we're going to invert it. So the next stage would be an inversion. We take 1 over that, and then we have this another complex number here, RE to the I psi. So I invert that thing, and I stretch it by capital R, and rotate it by psi. And then the last thing I do is translate it by complex number A over C. So we see that there are 7 maps. From 1 through 4. Is that 7? 1, 2, 3, 4, 5, 6, 7. Right. Okay, so the corollary of this basic fact is that LFTs take lines and circles to lines and circles. Because each one of those 3 maps do. Okay, the proof is proof. This is kind of a proof. 1, 2, and 3 take line to lines and circles to circles. So those are a no-brainer. It's inversions that can mix them up. 4 can mix them up, and sometimes it doesn't mix them up. I'll give you a picture proof of this. Oh, let's see. Let's do, here's a line going through the origin. 1 over z, that inversion, let's say that's angle theta, then there would be 1 over r e to the I theta is 1 over r times e to the minus I theta. And so you convince yourself that this would be, if this angle's I guess you can convince yourself if you want, if this angle is an alpha, this angle would be a minus alpha. So 1 over z takes that line to that line, and it turns it inside out. It blows 0 out to the infinity end, and it sends infinity down to 0. So it turns it inside out like that. But it sends a line to a line. And of course, 1 over z is its own inverse. So it does that going the other way. When I drew the graph of the complex exponential, I mentioned that if I have a horizontal line here and the origin here, then 1 over z sends that to a circle going through the origin. Let's see, if there's a spot right here, make it green. 1 over z, remember that would send that to something on the other, same angle, except below, like that. And how about a purple one over here? That's not a 0. Purple one over here. These would be symmetrically placed. Oh! What? How do I do that? Oops. What? So that's 0. Anyway, that takes a line to a circle. And the inverse is itself, and so that the invert being itself, 1 over z also takes that circle to that line. Okay. Question?
Just a quick clarification. Would these be circles or would they be ellipses?
Circles. That's the junior high analytic geometry you have to check out. Those are perfect circles, yeah. Okay, so that's an example of line to circle and circle to line. And then finally, you can take circles to circles. Let's see. What's the easiest one to do here? How about a circle not containing the origin? Then 1 over z would take that to a different circle not containing the origin. Maybe I should move it over here a bit. And I guess it would look kind of like a conjugate over here. Doesn't have to have the same radius. Could be much different. And of course, this is, once again, it's its own inverse. In the last case, actually when you start doing this, the junior high math, the calculations work in multiple cases. So it looks like a whole bunch of annoying cases to do, but they kind of pop out nicely. And let's see, the other possibility is you could have the origin in the circle. And then you'd have something like this, and that would map to something like, I should make it a different size maybe. I believe those are all the possible cases or pictures. So, proof, I guess it's high school analytic geometry. And if you look in a complex analysis book, there's ways to write out the formula for a circle involving complex numbers and their conjugates. And so it makes the calculations easier if you use complex analysis. Well, a fun fact that I should mention. On the Riemann sphere, lines and circles correspond to slices. So there's not two things, there's only one thing. And so slices get preserved on the Riemann sphere, which is the right place to think about linear fractional transformation. So here's the point at infinity. And remember the Riemann sphere sitting on the complex plane. Here's the origin. Here's a line. That line would correspond to a slice. Let's see, I'll do a slice. That's a slice. Slice with a plane. And of course, if I took the one going through the origin, that'd be like cutting the Riemann sphere in half. That would be a slice. That's maybe college analytic geometry. Let's see. A couple more lemmas. Maybe I can get them out of the way today. And next time I'll do some fun things with LFTs. Important thing to know, besides the line circle thing, is that a linear fractional transformation that fixes 3 points, it has to be the identity. Fixes 3 distinct points. Must be the identity. Let's see, why is that? It's also high school math. For proof. Let's say I have L of Zj equals Zj for three different J's. Z for 3 different points that are distinct. I'll take them to be in the finite complex plane. You can also make them include the point at infinity if you want, but I don't want. So what does that mean? That means A times Zj plus B over, let's not do the case C equals 0. You have to do those separately. Anyway, you look at that and realize, oh, that's going to give me a quadratic equation, namely CZJ squared plus D minus A ZJ minus B equals 0. And you look at that for a little while and think, oh, well, that's a quadratic equation that has 3 roots. Three distinct roots. How is that possible? Well, it must be that C is equal to 0. And D minus A would have to be equal to 0. And that would mean that B has to also be equal to 0. That's the only way you get a quadratic equation that has 3 distinct roots. Then everything's a root. And so let's see, since the determinant can't be 0, that means that, what does that mean? This one, determinant's not 0. So that means that D can't be 0. Okay, and now we see that A is equal to D, and D is not equal to 0, and so my L of Z is AZ plus 0 over 0 times Z plus A. A is equal to D. That's Z. So sure enough, it has to be the identity. And the case of AZ plus B is even simpler. So I guess if I was going to do cases, this is the case C unequal to 0. And the case C equals 0 is even easier. In fact, it might even be, if it fixes 2 points, it has to be 2 points are enough to make it the identity. But 3 points would work too. Let's see. So the corollary, if two LFTs agree at 3 points, then they're the same. At 3 distinct points. That's a no-brainer. Well, it's a lucky coincidence that 3 points determine a circle. Three points determine a circle. And 2 points determine a line. So 2 points in C plus the point at infinity, that's 3 points, determine a line. And we think of lines and circles as kind of the same thing on the Riemann sphere. So whenever something goes through the North Pole, it's a line. So let's determine a line. That's going to be useful to know. If you, let's see, am I running? I guess I have. Here's a useful LFT. Z minus A over Z minus B. That takes A to 0 and takes B to the point at infinity. And now if you think about what if I want to do slightly more than that? I would take Z minus A, that still takes A to 0, Z minus B. But what if I want to take a C to a point somewhere else? Then I would take here, let's see, C minus B over C minus A. That still takes A to 0. It takes B to the point at infinity still. But now it takes C to 1. And that's going to be a useful thing to know, because you can very often